Cool. So we've talked about DC circuits. On DC circuits, current and voltage rise together. They're in step. But in AC, things get a little bit more interesting. Components that store energy, like our capacitors and inductors that we've been talking about, cause a delay between the voltage and current. Today, we'll look at how that delay works and how it affects total circuit opposition. Cool, but first, we'll recap. So what form of energy does a capacitor store? So what type of energy are we talking about when we talk about a capacitor? What is the type of energy that we store? Yep, farads, electrical energy. I did talk a little bit about something else. Yeah, so we've talked about farads, which is the measure of capacitance. We've talked about coulombs, which is the charge. But what form does the energy get stored in? Yeah, Rex hit the nail on the head. So, a capacitor stores electrical energy in the form of an electrostatic field between its plates. So, you can look at it as electrostatic potential energy, but it is an electrostatic field. So, if you think about the charge that builds up on a metal surface, we call it a static charge. So, when you get that little shock from a metal surface, that's the release of the charge built up on the surface. And we call that static shock because it is an electrostatic charge. Cool. So, what form of energy does an inductor store? So, remember, an inductor is a coil of wire wrapped around a former, or it is a coil of wire essentially. Yeah, so you guys are on getting there on the right track. Yeah, so when we're talking about an inductor, which is similar to the windings of a transformer, or when we think about induction inside of the transformer, everything is done magnetically. So an inductor stores magnetic energy in the magnetic field created around its coil when current flows through it. So when we're talking about a coil or an inductor, it's electromagnetic or magnetic energy. Cool. So how does an inductor react when the current suddenly changes? So what kind of reaction does an inductor have to current change? Yep, self-induction is part of it. When we talk about reluctance, that's more about the reluctance of a material to become magnetized? All good, Andy. So long as you haven't managed to get yourself another shock, you're all good. Cool. So yeah, when we have current change, the inductor opposes the change and it generates an induced voltage, what we call a back EMF, that resists that change. It doesn't like change. It's that old Sparky that doesn't want to change. It doesn't want to get with the new technology. They just want to sit there doing the same thing they've done day in, day out. So the faster the current tries to change, the larger the opposition voltage becomes. So the quicker that culture changes, the louder the opposition old people get to that change. You can tell what kind of things we've been talking about in the workshop today. Cool. So yeah, that's what we were talking about last time, the difference between inductors and capacitors. So now we'll move into how it affects alternating current. So when we talk about DC circuits, it's a lot easier because the voltage and current's steady, and the only thing limiting current flow is the actual resistance itself. Once the inductor has built up its magnetic field, it just acts like a normal conductor. When a capacitor is fully charged, it doesn't have any more effect on current flow. It just allows current to flow past its terminals. But in an AC circuit, everything changes direction continuously at 50 hertz. So voltage and current are always on the move, building up, reversing, collapsing again. When a circuit contains an inductor, it stores the energy in a magnetic field, so whenever current flows. When that changes, the magnetic field also changes. And then the inductor, like we just talked about, produces a voltage that opposes that change. The opposition doesn't stop the current completely, but it slows it down. And as a result, the current waveform reaches its peak later than the voltage waveform. This delay is called phase displacement. So when we talk about phase displacement, we're talking about the difference between the voltage and the current. If an inductor current lags the voltage by up to 90 degrees, depending on how dominant the inductance is in the circuit. Cool. So we'll talk about the phase relationships and inductive reactance. So what is inductive reactance? So what do you guys think inductive reactance is? Cool. So when we talk about reactance, we use the symbol, well, basically we replace it with X instead of R when we're doing our calculations. So as the opposition to the rate of change in current, not the current itself. So it's not an opposition to current flow, it's the opposition to the change of current flow. So inductive reactance depends on frequency and inductance. So the formula relies on the inductance of the coil or the inductor and the frequency of the supply. So the formula, XL equals 2 pi times the frequency times the inductance. So F is our frequency in hertz, L is our inductance in henries. So when we talk about an inductor, the amount of inductance is measured in henries. So sometimes in the equation, you'll have to figure out what the inductance is. Sometimes they'll give you the inductive reactance, and you have to figure out what the inductance is. Cool. So if we increase the frequency, we get a greater inductive reactance. So inductors oppose high frequency AC more than low frequency. So they're opposed to the rate of change. So like we talked about, the more we change, the louder they get. So in a purely inductive circuit, the phase angle between the current and voltage is 90 degrees. So current lags voltage by 1/4 of a cycle. So by 1/4, that means when the voltage is at zero, current is at maximum. And when current is at zero, voltage is either at positive or negative maximum in the sine wave. So real inductors will always have some resistance though, so phase lag is always less than 90. So because the coils are made out of copper, there's always going to be some internal resistance in the coil. So we're never going to get a purely inductive circuit simply because to make an inductor, we need to use conductive wiring. Is this all making sense? Does anyone have any questions so far? I'm glad someone said something. Does anyone need me to not move the slideshow forward, or should I keep going? Okay, cool. So let's have a look at an example. So we have a 200 millihenry coil that's connected to a 60 hertz supply. What is the inductive reactance? So remember the formula from before, XL equals 2 pi FL. I want you guys to have a go at answering this question. So I'll give you the formula here. XL equals 2 pi FL. Just remember that the frequency is given to us as 60. All right, we've got one answer. Anyone else got anything different? Or everyone got about the same? Okay, I think I know what you did wrong, Sasha. Just remember it's millihenries, not henries. So we need to convert the 200. So yeah, when we input the values into the formula, it's 2 pi times 60 times 0.2 because it's 200 millihenries. We convert that into 0.2 henries. And then, yeah, 75.4 ohms. Sweet, all good, Sasha. Yeah, so just remember, whenever they give us a measurement that's in milli, micro, pico, any of those, we need to adjust our values. Sweet, just make sure you've got that calculation down. Yeah. Yeah. Odds are they will ask you about this in the capstone. And hopefully, more than likely, there will be at least a couple of what we call RLC, so resistance, inductive, capacitive circuits. So sometimes you will get a mix, and we will go over how to work them out as we go through the topic. Does anyone need me to leave that up, or can we move on? Cool. So now we'll figure out it using impedance. So if this coil has a small winding resistance of 10 ohms, the impedance would be, so Z equals the square root of R squared plus XL. So remember, because the the reactance and resistance are at 90 degrees opposing each other because of the way the inductance work, we treat it like a Pythagoras theorem triangle. So it's the square root of 102 plus 75.42. Okay, Troy, what values did you use? Did you remember to square? Is this even right? Right, bear with me. We go back to the previous slide, 75.4. Yeah, this. Yeah. That's what happens when you. Yeah, so it should be 100. And we should be using the impedance from the last one, so 75.4 times 75.4. Yeah, it shouldn't be 75.42 there. Yeah, we still get 76.1. So yeah, the values were just entered wrong into the equation. So it should have been 100 plus 5,685.16. Cool. So that's how it ends up. So yeah, remember it ends up looking like, if we were to draw it out, it would look like a triangle. And we will look at the triangles in a little bit. Cool. So now I've looked at reactance. Now we need to take a look a little bit at time and phasor representation. So when we're talking about time and phasor, so the time representation is the actual waveform if we were to draw it out. So with the actual line, I need to go to Teams. Cool. Yeah, can everyone see the whiteboard pen? No? No? No, you can't see the, okay, you can't see the DocuCam. Never mind. Cool, we'll go back. So when we talk about the time domain, so this is what the waveform looks like. So when the voltage is crossing zero, current is at its maximum because the energy stored in the magnetic field is being released. So this is what it would look like if we were doing a purely inductive circuit. So this is the relationship between voltage and current in an inductive circuit. So we can see that voltage is going up to peak and then going to zero at 180 degrees before the the current waveform. And the current waveform is at its peak, and then it's crossing down at zero, 270 degrees, which is 90 degrees behind the voltage waveform. So don't worry, if you're taking notes, just do a rough sketch. You can find these images on Google. If you just go inductive voltage current waveform, you should get an image similar to this come up. That way you don't have to worry about drawing it too perfectly. Yeah, you may be asked, so you won't be asked to draw one of these obviously in the capstone exam, simply because you will be doing it digitally, but you may be asked to identify parts of it, or you may be asked to identify whether this is an inductive or capacitive waveform. Then we move on to phasor diagrams. So might be a little bit hard to see, but the voltage is drawn as the reference line on the horizontal. And then the current vector, because it's a vector diagram or phasor or vector diagram, lags behind the voltage by a pure 90 degrees for a pure inductor. So it's the blue vertical line. But obviously in a practical coil, like I've mentioned, the current vector will lag slightly less, maybe 80, 85 degrees due to the coil's resistance, and depending on what other resistances are in the circuit with it. So what happens to the current waveform as the frequency increases? So remember back to the formula. What part does frequency play in the formula? Yep, so the inductive reactance increases. So what happens to the current waveform? Yeah, it will go up and down more often. Yeah, well, not more resistance. Remember, resistance is the reference line, and our inductance is the upright. So the hypotenuse is going to get longer, which is the representation of impedance. So if our impedance is increasing, what's going to happen to our overall current level? Yeah, so as the frequency increases, we get an increased inductive reactance because XL equals 2 pi FL, which means the inductor offers greater opposition to the current flow. The current amplitude decreases, so the amount it goes, so it does go up and down more often, but the total distance it goes up off the reference line decreases. So the current waveform will lag further behind the voltage as well because we have more of an inductive load than a resistive load. Because the inductance goes up, but our resistance stays the same. The resistance is not affected by the frequency of the waveform. So our resistance will remain constant. So what happens if an inductor resists change in current? What happens at zero frequency or DC? Yeah, pretty much nothing happens. So at zero frequency or DC, there's no changing magnetic field. So the inductor behaves like a simple piece of wire with low resistance only. The reactance becomes zero, so XL equals zero, and current can flow freely once the magnetic field has already built up. So yeah, if we've got no frequency, we've got no changing current, the inductor just behaves like a resistor. Cool. Why is the phase difference slightly less than 90 degrees in a real coil? Not so much anything to do with the efficiency. Not power factor. We have talked about it. So the phase difference isn't always going to be 100% 90 because of something to do with the coil itself. So think about what the coil is made of. Yeah, that has something to do with it. It comes down to the fact that a real coil contains both inductive reactance and resistance in the wire itself. Because the coil is made up of a bunch of wire, it has resistance no matter what. So, because of this resistive component, the current is not perfectly 90 degrees out of phase with the voltage. It's slightly less, typically around 70 to 85%, depending on the coil's resistance. So we have the inductive nature of the coil in the magnetic field, but because of that inherent resistance in the wire, we're not going to get a pure 90 degrees out of phase with the voltage. So how could you represent this combination of resistance and reactance graphically? Yeah, we could do it that way. So, so graphically, so some form of graphic or some kind of geometrical shape that could represent the combination of resistance and reactance. Yeah. At the end of the day, electricity loves triangles, and the relationships between a lot of things in the electrical world come back to triangles. Yeah, it's like the electrical version of trains. Cool. So you can represent it using an impedance triangle where you have resistance R as the adjacent side or the flat long side. The inductive reactance is the opposite side, the upstand, and the impedance is the hypotenuse. So the triangle visually shows both the magnitude and the phase angle how far the current lags the voltage. So if we were to actually measure it out and draw it, it would show us this. Cool. So hopefully this comes through. Oh, hope everyone can see that. So this is a program called Every Circuit. So this is a way of us showing how a circuit operates. So if I So it is a bit laggy, I'm sorry. But as you can see, the waveform here, so the green line there is representing our current flow through our coil, whereas our blue line is representing our voltage. So you can see there that the green line is running slightly behind. So if I were to take this inductor, and I was to increase the amount of henries, so you can see there I've increased the inductiveness, and so the AC waveform went down a little bit. Now it's back up. You can see how much further behind it's lagged. But then if I increase it again, so you can see there's a slight delay because of the increase. So the current has dropped a little bit. But you can see it's slowed down even more behind. So eventually we get to magnetic saturation. But what I can also do is I can change the frequency of the supply. So you can see there we're at 400 hertz now. How little change in current flow there is, how small the current change is. But look at how quickly it's moving. So I've reduced the current. So we're in microamps now. Drop it back down to 200 hertz. So you see, just by playing with the frequency, how much it can change things. Cool. So some summary points of what we've talked about so far. So inductive reactance increases with frequency. Inductors cause the current to lag up to 90 degrees, but never quite 90 because of the inherent resistive nature of a coil. Real inductors have both resistance and reactance, which combine to form our impedance. So this combination can be represented by a phasor diagram, or it can be calculated using Pythagoras theorem. So we can draw it to scale and measure it and figure out the angle that way, or sorry, the impedance that way, or we can calculate it using Pythagoras theorem. I'll give you guys a moment to get those notes down. Anyone have any questions about what we've gone over so far? Even anything small? Any question's a good question. Also, did everyone get sent out a survey today from Skills? You probably would have got a text message around about between 3 and 4 o'clock. No, you do not have to do it. It's completely optional. I mean, That's not this. Yeah, I'm just going to not comment on that. Yeah, there's quite a bit of manual marking, but at the same time, we need to do it because we need to ascertain that you guys are understanding more than just multi-choice questions. So that's why they're doing the manually marked big answers, because it shows that you can find and understand, or at least know where to look for the information that you need. You understand enough to relay the information in the SCORM packet to the what you're doing. Right. Okay. Okay, can everyone see whiteboard behind me? Cool. All right, so yeah, we'll go through, I'll draw the impedance triangle, and then I'll talk about a little something else while we're at it. Wait for the projector to start up. So there is a little document camera here that is supposed to work, but unfortunately it only seems to work if you are using actual Teams, not screen sharing. Come on. Give me the option to use the whiteboard, please. Cool. So our impedance triangle. So we have our resistance. So pure resistance. Flat line follows the voltage wherever we go. Then we have our reactance. In this case, our inductive reactance. So our XL. Doesn't look very nice for that. So our X, lowercase l. So we only have a small amount of inductance versus the resistance that I've drawn. So now we join the two with our hypotenuse, or Z for impedance. I'm just going to turn the lights off so you can see a bit better. I think I'm going to change it anyway. Let's go with green. Yep, that's better. So yeah, now we have our resistance, our impedance, and our reactance. So this is the relationship. So we're always going to have a 90 degrees here. That's always going to be 90 degrees. But once we start talking about impedance, we then start talking about our phase angle. So we will look at this a little bit more in detail later, but this here is our phase angle. So this is how we figure out how far behind our current is going to lag our phase. So if I was to draw another one, so with this being our resistance, and this being our inductance, and I'm very bad drawing on this board, this would be our impedance. And then obviously our phase angle has gotten a lot bigger. So this is most likely going would be what the phase angle would be inside of an inductor, but this is closer to what it would be in a real life circuit. Does this triangle all make sense to you guys? So we probably will come back to the whiteboard a little bit later. Now we'll carry on. Cool. So now that we've got those points down, we can start looking at our phasor representation, vector addition, and our impedance. Cool. So what we know so far. So we'll pull together what we've already known. So we've seen that resistance opposes current flow all the time, converting some energy to heat, while inductive reactance opposes changes in current by building and collapsing a magnetic field. Both of these oppose current, but they do it in different directions. Resistance acts in phase with the current, and reactance acts at 90 degrees out of phase. So if we imagine these two effects as sides of a right angle triangle, like we drew on the board, resistance R is the adjacent side in line with the current, and then reactance XL is the opposite side at 90 degrees. I will come back to the slide in a sec. So that leaves one remaining side, the hypotenuse, which represents the total opposition to current flow in the circuit. We call this total opposition impedance, which is noted as a Z. So impedance combines both the magnitude of resistance and the timing effect of reactance into a single quantity. That's what we use in AC circuits instead of resistance alone, because it accounts for both the size of the current and how far behind the voltage that current lags. So I will go back to the previous slide so you guys can get that down as notes, and then we'll move back to the second one. I just wanted to get that all out in one explanation. So this is why when we talk about our earth fault loop, we talk about earth fault loop impedance, because we're taking into consideration the inductive nature of the transformer itself. Because if you go, I think we've talked about it, the earth fault loop, if you're testing it at a socket outlet, we're measuring the impedance of the circuit from that earth back to the main earth bar, through the MEN link, down the main neutral conductor back to the transformer, through the winding of the transformer to the phase, down the phase, through our main switch, through our circuit protection, down our phase conductor to our socket outlet. So that is a long circuit, and yet we get something a lot of the times like 0.56 ohms. Because it is impedance and not resistance, it changes the equation. So remember, whenever you're doing earth loop impedance, you're measuring it all the way back to the transformer and then all the way back to you along the neutral and phase conductors. All right. Does anyone need any more time on this, or can we move back to the next slide? A little bit? Cool. Yeah. Oh, yeah. Here we go. Yeah, whenever we're talking about the total opposition to current flow in an AC circuit, we're always talking about impedance, because we have to take into account the reactance of the circuits, whether that be inductive or capacitive, like we'll look at in a little bit. So does anyone know why we do earth fault loop impedance tests as part of our testing when we do our installation testing? Just while I wait for people to write down what's going on, I just thought we'd talk a little bit about what we can use impedance for. So what are we actually checking when we do our impedance tests? There is, well, the total opposition. Yeah, so we're making sure that the protection can trip in time. Yeah, so we're making sure there's enough current flow that if there was a dead short at that power point or whatever point we're testing, it's going to trip the circuit protection protecting that circuit. So so we can check when we do the test versus table 8.1 and ASNZS 3000 that we are, so they give values in that for us to reference so we can say whether it is a pass or a fail. And speaking of 3000, if you impedance testing batteries, I am not sure about batteries. It's not an impedance test in the batteries. I guess because of the chemical nature of the battery, it changes things. And because I think the batteries kind of act like capacitors, that's why they do impedance testing for them. But that's kind of my best, I'm going to say, guess for batteries. But yeah, just in case you guys weren't aware, it's official. We're getting ANZ's 3000 2018, which means when you guys do your regs classes, you will be doing it to 2018. So if you guys want to get a copy from the standards portal, make sure you download the one that is Amendment 3, or you download the latest version of it. Something ridiculous like 200, 300, 400 and something changes. But you guys won't need to worry about that because you'll start learning 2018. We've done a little bit about it throughout the years. Yes, when you get to year 3, you get a physical copy. So ETCO will print you a physical copy when you get to year 3, along with some other standards. You can order them from the print shop, but they are quite expensive. So, anyone need more time or next slide? So right now you can do either or, simply because I've been checking against 2000 and 2018 when you guys have been answering your questions, and for the most part, nothing's changed too much in damp situations. It's more to do around EV chargers, protection, and switchboards. Cool. So some key points so far. Resistance or reactance are at right angles to each other. The total opposition or impedance is the hypotenuse. The impedance is measured in ohms, just like resistance. It's calculated using Pythagoras theorem, which we've used just before. Z equals the square root of R squared plus XL squared. So this is stuff we've already gone over. We're just recapping it as we go through. Impedance represents both the magnitude of the total opposition and the phase angle between the voltage and current. The phase angle indicates how much current lags the voltage. So the angle is, if we look on the graph that was plotted in the time diagram, how far it lags behind it. So small angle, mostly resistive. Large angle, mostly inductive. 0 degrees, purely resistive. 90 degrees, purely inductive. But remember, a coil cannot be purely inductive. But we can use Ohm's law for AC circuits. Current equals the voltage divided by the impedance. So it's the same as the resistive circuit, only we've swapped the resistance for our impedance. So does this all pretty much make sense? Is there anything that's not quite getting there? I need to know what's not making sense so I can fix it before we get too far into this. Cool. So here is a good question. So we have a 230 volt supply and it feeds a coil with a resistance of 30 ohms and an inductive reactance of 40 ohms. We need you to find the impedance, the current, and whether the circuit is more resistive or inductive. So don't put the answers in the chat. Just when you've figured out 1, 2, and 3, just put a random emoji into the chat. Don't worry, the chat doesn't, as far as I know, it doesn't show up on the video. So it's all good, whatever you want to put in there. Yeah. So with the skills survey, guys, don't worry. I also got sent one because I am technically doing a skills course for something else. Yeah, Tim, that's about how I felt when I got the text message, because they have not been very good. But it's not a eco skills course that I'm doing. It's a skills course. So they've made a few mistakes. Oh, that's a throwback, Sasha. The old paperclip. All right, I'm going to do this on the board. Cool. So the first thing it wants us to figure out is our impedance. So first thing we're going to do is we're going to punch in our equation. So Z equals the square root of R squared plus X squared. In this case, it's XL, but we can just use X. So that results in the square root of, so our resistance is 30 ohms. So easiest way, if you don't have a calculator, you can just go 30 times 30, because square just means times itself. So that ends us with 900 plus, so our impedance or our reactance, sorry, is 40. So 40 times 40 gives us 1600. Oh, so that means it's the square root of 2500, which gives us 50 ohms. The other way we can remember this is the 3-4-5 rule. I think I talked about this a little bit last year. If we have a triangle with one side that is 3 and one side is 4, the resultant hypotenuse will be 5. So 30, 40, 50. So now we need to work out the current. So our I equals V divided by Z. So they've given us the voltage of 230 divided by 50. Which gives us 4.6 amps. Cool. And whether the circuit is more resistive or inductive, well, the reactance is 40, so it's more inductive than resistive. That's more of a word question. So we go back to our PowerPoint. So the solution, yeah, so that's what it looks like. Nice and neatly written out versus what I put on. So is that what everyone else got, or did anyone get anything different? Yeah. Yeah. So once you start doing the calculations a few times, it does kind of get pretty straightforward. All right, so now that we've looked at some of the calculations, we can look at a little bit of interpretation. So the impedance is 50 ohms, which is greater than either R or X alone. Because XL 40 is more than the resistance of 30, the circuit is deemed to be more inductive, meaning the current lags the voltage noticeably. Cool. So on a right angle diagram, base 30, R vertical 40, diagonal 50 ohms. So we'll go back to the whiteboard. I kind of already shown this before, but if we look at it, if we have a longer base, the angle is shorter. But obviously, if our inductive nature is more than our resistance, we have quite a large phase angle. Cool. So if resistance increases but reactance stays the same, what happens to the phase angle? Yeah. So basically, the phase angle will decrease because that bottom is getting longer than the upright. So the reactance hasn't changed, but we've added a resistor or we've added a resistive load. The phase angle will decrease. So it means the circuit becomes more resistive and the current waveform moves closer in phase with the voltage. Cool. So what would the triangle look like for a purely resistive circuit? Well, not so much a vertical as a horizontal line. So a purely resistive circuit, no reactance. So the opposite side, X of the triangle disappears. It collapses into a straight line, showing voltage and current in phase. So the phase angle equals 0. So on a phasor diagram, both voltage and current vectors sit on the same line. So it's stopped being a triangle and now it's just flat line. How can you tell by looking at a phasor diagram whether a circuit is inductive or resistive? Sorry, is more inductive or resistive? Yeah, so basically in a resistive circuit, the voltage and current phasors are in line. There's no phase shift. In an inductive circuit, the voltage phasor leads the current phasor, showing a lagging current. The larger this angular separation, the more reactive, in this case inductive, the circuit is. Cool. So a bit of a summary of this section. So resistance and reactance oppose current in different directions. So they combine at 90 degrees. The total opposition or impedance Z is found using Z equals the square root of R squared plus XL squared. Impedance determines how much current flows and how far it lags behind voltage. The ratio of R to X defines the circuit's phase angle, theta. So, phasor and triangle diagrams provide a clear way to visualize the relationship between resistance, reactance, impedance, voltage, and current in AC circuits. I'll give you guys a bit of time to get those summary points down. Okay, does anyone need a bit more time? Cool, sweet. So now that we've talked about that, we'll talk about phase angle and we'll talk about capacitive reactance. So we've built our impedance triangle with resistance along the base, reactance, in this case XL is the upright, and impedance Z as the hypotenuse. So the triangle doesn't just show us the size of each part, it shows us a timing relationship between the voltage and current and the AC circuit. So that's the angle between R and Z, and the phase angle represented by theta. So when the circuit is mostly resistive, the triangle is flat. Theta is small and current is nearly in phase with voltage. When the circuit is mostly inductive, the triangle stands tall. Theta is large and current lags the voltage quite a bit. So we can find the phase angle using the sides of the triangle we already know. Since Z is the total opposition and R is the in phase part, the ratio between them shows us how far current lags behind voltage. So we can use cosine theta equals R over Z. So the bigger the resistance compared to impedance, the closer current and voltage are to being in phase. The bigger the reactance, the smaller RZ becomes, and the further the current lags. So cosine of theta. So when we divide R by Z and we use cosine of that number, we get the angle. So we'll do an example. So we have a 230 volt circuit that has a 30 ohm resistance and 40 ohms of inductance. Cool, so now we're going to find the impedance. And this time we're going to look for the phase angle. So we already kind of know the impedance for this one because we looked at it earlier. So we go back to this one. We already have our impedance from the last one. So 30 and 40. So we already know we have an impedance of 50. So now we can figure out our phase angle. So we're going to take our resistance of 30 and we're going to divide it by our impedance of 40. What does that give us? Yeah, it gives us 0.75. Yes, you're right. I had thought 40 stuck in my head. So it gives us 0.6. I had my head in the clouds. Cool. So earlier, we looked at the formula and it had cosine of the angle. So this is equal to 0.6. But we need to find the phase angle. Does anyone know how we're going to do this? Does anyone remember back to our Pythagoras theorem days how we are going to figure this out? Yeah, we're going to go cosine to the -1 or inverse times 0.6. Trigonometry, yeah. Not Pythagoras theorem. Thank you, Fergus. Pythagoras is all out the sides. Cool. Yeah, 53.13 degrees. So, this number here also represents something else. Does anyone know what else this little number of 0.6 represents? No, this is our power factor. So when we're talking about, so we will look at the way this works in terms of power, but when we go back to the triangle, later on we'll look at how we can replace resistance with power. We can replace XL with our VA reactive, and we can replace our Z with VA. Also known as our S or apparent power. These are things we will look at as we go through the topics. But that is something to be aware of as we go forward. Cool. So yeah, our relationship is 0.6, and we figured out the angle was 53 degrees or 53.13. Cool. So from the ratio RZ 0.6, we can see it's a fairly inductive circuit. Current lags the voltage quite a bit. The smaller the ratio gets, the greater the lag between the voltage and current. Cool. So the cosine relationship we looked at gives us a practical way to describe how much current lags without needing any complex maths. So yeah, later when we talk about power, we'll see it becomes really important and directly represents how efficiently electrical energy is being used. So now that we've looked at the phase relationship, we can start to look at capacitive reactance. So because of, yep, cool. So everything we've done so far has been based around inductors, where voltage leads the current, lags the current. Hold on, I'm going to fix this because it's going to annoy my brain. Yeah, inductors make voltage lag the current. But in many real circuits, we also have capacitors, and they have almost the exact opposite effect. So a capacitor stores energy in the electric field between its plates, and when the voltage changes, it resists that change by drawing or supplying current. Because of this, in a capacitive circuit, the current leads voltage. The waveforms swap positions compared to an inductor. So a capacitive reactance has the opposite effect to what an inductor has. So where an inductor forces the current to start, resists the change in current flow. As soon as the current level starts to drop, the capacitive draws more current from the supply depending on what way the voltage is going. So the other way to look at it is that the current sees the capacitor as a dead short and wants to rush in there and fill the void. It wants to rush through there because it sees the easy way out. Of course, it's a false, it's a lie that the capacitor is telling the current because there's no actual conductive path. Cool. And so we get the formula XC equals 1 over 2 pi FC. The other way we could draw this is 2 pi FC to the power of -1. Cool. So we describe the opposition to changing voltage as capacitive reactance, and we symbolize it with XC and calculate it by this formula. So it's the reverse of the inductive formula. So as frequency increases in this, our reactive capacitance would actually get smaller, meaning the capacitor allows more current to flow. So in an inductor, higher frequency, more opposition, and a capacitor, more frequency, less opposition. Does that make sense, guys? Does anyone need me to go back a slide? Yep. Cool. So some key points to know. So the phase angle tells us how far voltage and current are out of step. So we still have cosine theta equals RZ. So as a resistance increases, the angle will decrease. So inductors cause current to lag voltage. Capacitors cause current to lead voltage. Capacitive reactance decreases as frequency increases. So XL increases with frequency is equal to frequency. XC is equal to 1 divided by frequency. So they have the opposite effect. 100% remember what that alpha fish means. But basically it's saying XL is proportional to frequency, whereas XC is proportional to 1 over the frequency. Cool. So if we added a capacitor to the same circuit we've been working on, what do you think would happen to the phase angle? We go back towards 0. Yeah, so basically, if we were to add a capacitor into the circuit that we'd already been working on, it would bring the current closer to the voltage or would cause it to lead the voltage depending on the size of the capacitor that we introduce. Cool. So we had a look at this circuit before with just the inductor in the circuit. So here's what it looks like when we have a capacitor. So you can see there the green line, which represents the current, is ahead of the voltage. The current is going before voltage in this circuit because of the way the capacitor works. Now, if we go look at the next one, sorry, powering up, come on. You can see here the orange, which is the capacitor, is leading the voltage, which is the blue, and the green, which is the inductor, is lagging behind. So right now it looks like they're all pretty much in sync in terms of the current flowing through the inductor and the capacitor. But what happens if I change the frequency of supply? So we can actually do that in real time. So I can change the frequency. So if I was to decrease the frequency to 20 hertz, you notice there the inductive current, doesn't have as big of an amplitude. It's kind of hanging around the less than 100 milliamps, whereas the current in the capacitor, the current in the capacitor has dropped quite a bit because it is more reactive. But if we increase the frequency, other way, we're getting more current flow through the inductor, and the current in the inductor is, through the capacitor, and it's pretty close to the voltage. So the voltage isn't lagging behind the capacitor as much anymore. So we have less reactance. So by half the frequency, the voltage is lagging quite a bit behind the current flowing through the capacitor. If I then multiply it to 3, let's slow down the speed a little bit. You can see there the voltage is catching up to the current inside of the inductor, sorry, inside the capacitor, but the current flowing through the inductor has dropped quite a bit. So if I go back to the supply and I drop the frequency back down to 50 hertz, everything is kind of evened out again. I'll increase the time frame. So the current change between the inductor and the capacitor is pretty much the same. Everything's equaled out. But if I then drop the frequency again down to 30 hertz, there's a lot more current flowing in the inductor, and the inductive reactance is getting closer to the voltage. That's a good way of viewing the waveform as it goes. Cool. So, summary of that section. So the impedance triangle relates R, X, and Z, total opposition to current flow. The phase angle shows how far the current lags or leads the voltage. So for inductors, current lags, cosine theta equals R over Z. For capacitive, current leads. The angle is still the same, but the phase would be in the opposite direction. So if we were to draw our triangle again, it would be upside down. So capacitive reactance, or XC, behaves inversely to the inductive reactance in terms of frequency. So if we would go back to our triangle, instead of drawing it, so if we were to draw our line here for our resistance, our XC would go down because it's leading our voltage, but our impedance would still be the same, the hypotenuse. So if we draw the triangle, we draw the XC going down and the XL going up, because the resistance follows the voltage, which is our horizontal reference line. Does that make sense to everyone? Cool. If anyone has any objections, I'll move on to the next section. Cool. So, combined reactance and vector summation. So now that we understand inductive and capacitive reactance on their own, we'll take a step and look at what happens when both are in the same circuit. So inductive reactance causes the lag, like we've talked about, and capacitive causes it to lead. This means their effect act in opposition to each other. So they have the opposite effect. Cool. So XL points upwards, representing the lagging current. So we were to draw it on a phasor diagram. We have our horizontal reference line. This is our voltage or our resistance. So we have our vertical, which is our inductive reactance, or XL. And then downwards, we have our XC, representing leading current. So XL represents the lagging, XC the leading. Because they're on the same vertical line but opposite in direction, we can combine them by subtraction. Cool. Cool. So if XL is greater, the circuit behaves inductively, current lags. If XC is greater, the circuit behaves capacitively and current leads. So the total net reactance of the circuit becomes X equals XL minus XC. Because they work in opposite of each other, we subtract. So it doesn't matter whether you go XL minus XC or XC minus XL. It's going to tell you this, it's going to give you either a whole number or a negative number. Either way, it's going to tell you whether it's more inductive or more capacitive, and it's going to tell you which way to draw your triangle if you need to. Cool. So some key points. Inductive and capacitive reactance are vector quantities that act 180 degrees apart, so they are complete opposites of each other. The net reactance, or X, is their difference, not their sum. We need to make sure we don't add them together. So this net reactance combines with resistance to form the total impedance, and we can write it as this calculation, with impedance, or Z, being equal to the square root of R squared plus XL minus XC squared. So it doesn't matter whether you end up using the smaller number minus the bigger number or the bigger number minus the small number. As soon as we square the number, it will turn itself into a positive number. It's just the way that the calculated mathematics work. The circuit's phase angle depends on which reactance dominates. So if XL is bigger than XC, we will have a lagging current because it's an inductive circuit. If XC is bigger than XL, we will have a leading current because it is a capacitive circuit. If XL equals XC, they will be perfectly balanced and we will get resonance, voltage and current in phase. Does anyone need me to go back to the previous slide? Cool. So once we start to understand how to use these calculations and these theories, then we can start looking at questions that involve transformer windings where we know the inductive nature of the winding itself, or how many henries it puts out, the resistance of the winding, and then we can figure out the power factor, current, voltage, all those fun things. I say fun, but it doesn't actually sound fun, does it? Cool. All right, I'll leave this up for a little bit. No, it doesn't sound fun, I know. It's a lot of maths, it's a lot of calculations, but we need to know how to do it because it becomes part of it is understanding is the main part, but you need to be able to do these calculations in order to pass your year 3 or national theory exam. There are some of you who, once you finish your year 3 theory, will never use this stuff again, or there are the strange people like myself who end up deciding to teach it for a living. Other than, well, the not this stuff specifically. Some stuff we do use on site when we're trying to figure out why a piece of equipment is acting in a certain way. But yeah, we have a sticker on the wall inside of the tutor area that says, "You don't have to be crazy to work here. Don't worry, we will teach you." Basically implying that you don't have to be crazy to work here, but once you start working here, yeah. There's also one on the door as we leave our tutor smoker area that says all staff must stop crying before they return to work. Oh, does anyone need me to stay on this, or can I move on? It depends what block course we've got on, Aaron. Cool. Cool. So, the question. So, a 230-volt AC supply feeds a series RLC circuit with a resistance of 25 ohms, an inductive reactance of 40 ohms, and a capacitive reactance of 30 ohms. So we want you to find the net reactance, the impedance, and the current. So once you've found all three of those, again, just post a random emoji in the chat, and then after we get a few, I will then start working through it. Cool. So 230-volt AC supply. So we need to find the net reactance. So we know, wrong color. X equals XL minus XC. How am I forgetting which way a C goes? So we have an inductive reactance of 40 minus 30. Nice, easy math. X equals 10 ohms. And we will put it as lagging. So the reason I'm putting it as 10 ohms lagging is to remind myself that this is a lagging and it is XL. So we are going to find the impedance. So Z equals square root of R squared plus X squared. So our resistance is 25. So 25 squared plus 10 squared. So square root. So square root of I'm going to write out each step because my brain. Six to 5 plus 100 to square root of 7 to 5. So Z equals 26.93 ohms to 2 decimal places. So that's our impedance. Then we move on to current. So I equals V divided by Z, which in this case is 230 divided by 26.93. Which gives us 8.54 amps to 2 decimal places. Anyone get anything different? By that I mean completely different or completely out the gate. I'll bring us back to the PowerPoint. Cool. They got pretty close answers, but their calculator might have been slightly different. So the thing with the online tests and the capstone, you probably won't have to show your working. In all reality, when you come to do the capstone, because it's not created by us, it's created by outside, you will basically be given a question, you'll work out the answer, and there might be one that's, look, we got 8.54, they got 8.55. So if you're off by 0.01, it's that answer. So more than likely, you'll have multi-choice questions for the capstone. As far as the assessment for this unit, I haven't looked at the questions yet, but I do not believe if it's a manually entered question, you will probably have to show your working. But this, what we've got on the board is fine. So z equals square root of r squared plus x squared, which equals square root 25 squared plus 10 squared equals 26.9. That's perfectly fine. I've shown my formula. I've identified the values, and then I've given you the answer. That's perfectly fine. You don't have to do every step like I did. That's just the way my brain works. Cool. So this circuit is slightly inductive because XL is bigger than XC. So the current will lag the voltage by a small angle. We could actually figure it out, but it doesn't ask us to. If XC were to increase to 40 ohms, the two reactants would cancel each other out, leaving only resistance or resonance. Cool. So if I increase the capacitance of the circuit, what happens to XC? We've already talked about that. What happens if I increase the capacitance of the circuit? What happens to XC? So if I've increased the capacitance, remembering back to our formula, what's going to happen to our capacitive reactance? So we've increased the capacitance, so we put a bigger capacitor in. What happens to our capacitive reactance? Anyone else got any answers? Okay, yeah. So we will get a decrease in our capacitive reactance because our capacitive reactance is equal to 1 over 2 pi fc. So if we increase our frequency or our capacitance, we've increased the number we're dividing 1 by. So our capacitive reactance actually gets smaller the more we increase our capacitance. So the bigger a capacitor we put in, the worse, the less capacitive reactance we get. So when XL equals XC, what does that tell us about the angle or our phase angle? When XL equals XC, what does that tell us about the phase angle? We have no angle, we have balance. What else do we have? I've mentioned one other word tonight. What other word would we have? Yep, we would have resonance. So why might resonance be both useful and dangerous in electrical systems? So does anyone want to take a guess? Just take a stab in the dark. Why might resonance be both useful and dangerous in electrical systems? I don't think we have to worry about too much overcurrent because it's basically just having a resistive load. Inrush current's high. So we'll look at this in a bit more detail in probably next session. But basically, when we start to get resonance and we get all kinds of other weird harmonics, and that's where things start to vibrate in weird ways. We get stray currents, stray voltages, current spikes, voltage spikes, and that's kind of where things start to blow up. So we never want resonance when we're talking about inductive and capacitive circuits. Having a purely resistive circuit is one thing, but if we have a resonant circuit with an RLC, resistive, inductive, capacitive, that's where things start to get a little bit blow up. Cool. So in summary, so inductive and capacitive reactance act in opposite directions on a phasor diagram. Their effects combine by vector subtraction. So they don't add together, they don't multiply, they're not a sum, they are a subtraction. The total impedance of an RLC circuit is given by this formula. Z equals the square root R squared plus XL minus XC squared. This is all stuff we've already got notes down. The circuit's behavior depends on which reactance dominates. So XL more than XC, inductive, we get lagging current. XC bigger than XL, capacitive, we get leading current. And then XL equals XC, we get resonance, where current and voltages are in phase, and impedance is purely resistive. But again, we also get harmonics, and we'll look at that in a little bit later. Everyone's got everything in their notes already. I don't need to go over the last two slides. Cool. We're in the home stretch, guys. So we've done all of the main teaching stuff. So now we're just moving into the recap. So far we've seen how resistance, inductance, and capacitance all shape current flow in AC circuits. When we bring them together, we get some really interesting and powerful behaviors. In our next session, we'll take this one step further and explore what happens at that balance point, resonance, where inductive and capacitive reactance perfectly cancel each other out. Cool. So some recap points. Inductors cause current to lag, capacitors cause current to lead. They are opposites of each other. The only difference being that inductors will have more internal resistance in them than capacitors do. Capacitors almost act like a dead short. They are essentially an open circuit, not a dead short. So if you try and get a resistance across a capacitor, you will probably get mega ohms of anything. Cool. So reactance, whether it's capacitive or inductive, adds a phase shift, not power loss. Some people look at it as a power loss, but it is not technically a loss. The impedance combines both the resistance and reactance into the total circuit opposition for AC circuits. Remember, we don't have impedance in DC except maybe in batteries. We only have it in AC circuits. The ratio R divided by C defines the phase angle or the power factor, like we'll look at in later sessions. The inductive and capacitive reactance can cancel each other out. So if we have a circuit that's too inductive, we add a capacitor. So what happened? What used to happen back in the day with all of these big factories, with all of these motors that were turning on, they would need capacitor banks connected to the main supply, and they would click in these capacitors in and out depending on how much inductive reactance there was in the circuit. So it used to be that we had these huge capacitor banks with all these inductive motors, but now that a lot of the motors are switching over to other forms, or we have other loads. So some big apartment buildings, but when they first started being turned on, they had so many LED lights in them that the power factor went the opposite way. So when we first started bringing in these massive buildings with LEDs, we had a phase angle shift the other way. And people were concerned we'd have to start putting resistor banks into apartment buildings. So, what causes the current to lag the voltage in an AC circuit? So it's just 3 quick questions to round out the night. What causes the current to lag the voltage in an AC circuit? XL being then higher than XC? Yep. Inductive loads, yeah. Yeah, it's basically just inductance in general. So it's the inductive reactance of a coil or inductor causes the current to lag behind the voltage. So yeah, as it changes direction, the magnetic field resists the change and dumps a back EMF, which delays the rise and fall of the current relative to the voltage. Cool. What does R divided by Z tell us about the circuit? Yep, it gives us the phase angle or power factor. Yeah, so it gives us the power factor of the circuit expressed as cosine theta. So it shows us how much of the current is doing useful work, so the resistive component, versus how much is being used to build and collapse the magnetic or electric fields, the reactive component. Cool. The value close to 1 means mostly resistive and efficient. A smaller value means more reactive, less efficient. Cool. When XL equals XC, what is the circuit condition called and what happens to the phase angle? So when inductive reactance equals capacitive reactance, the circuit is at resonance. At resonance, the two reactances cancel each other out, leaving only resistance. Phase angle becomes zero, current and voltage are in phase, behaving like a purely resistive circuit.